Okay, so let us continue. Uh, so we have seen the registers. We have seen shift registers where you can have serial in parallel out, parallel in parallel out, all these modes. And they basically have if it is a parallel in, they have a load control. Once the load control is on, the data is input. And maybe you have a read control. When the read control is out on, you can get the output. Similarly, you can have an propagate control where in a serial input or a serial output, the values propagate. And we have seen that it's a sequential circuit, even though we have not worked on shown the design of the sequential circuits. It's very easy. You can draw the state transition diagram of the cascaded flip-flops in a register, and you can easily write down the logic for the state transition, depending on what kind of shifting you want. There is another sequential circuit, which is kind of a group of a cluster of flip-flops that is used, which is a counter. So for example, the simplest example is something called a modulo K or modulo 8, let's say counter. So you have states from S0 to S7, and depending on the clock input, it will transition between the states. And after you when you count till S7 or maybe S0, you output 1. So when you reach S7, you produce an output of 1. Okay, and since it is a 8-bit counter, probably you will need 8 counter. You will need 3 bits to represent the states. You can have other logics also. You can have say modulo 10 counter, which is modulo 8, and then when it modulo 10, when it reaches 10, you have 4 bits. When it reaches 10, it moves back to S0. So so usually the counter's state transition diagram will look like a circle. Usually it will look like a circle. Again, I am not going into the combinatorial details except for this simple example. So here you can see if you have a modulo 8 counter, you can basically count, you can basically cascade or not cascade, you can connect flip-flops, in this case SR flip-flops with the same clock. And then the transition is, if you look up the truth table from here, you can write down the logic for the S and R outputs, depending on the inputs. You can write down the logic and the intermediate states. Okay, so this again, I am not going into the details. You can design the combinatorial circuit. And these counters are very commonly used in your ALU and others. These are kind of used anywhere you have a loop or maybe where you have things like you want to look at, there's something called a program counter inside a CPU, which will look at the next instruction to be executed. Or if you want a timeout in any place, such counters would be useful. So it's a very useful piece of hardware required in many digital circuits. The same counter, depending, you can change the mode of the counter, up counter or down counter. Again, counters can also be synchronous and asynchronous. You can either have a clock or they can transition between states, between counts, depending on some input. They can either be synchronous or asynchronous. So this is a simple circuit for such a up-down counter, which can be easily implemented. Okay, so these are the two different modes of the counter. All right, so coming to the conclusion, so we have seen a number of different circuits that we have studied using either sequential or combinatorial. We have studied functional blocks like adders, comparators, multiplexers. We have seen storage units like say registers and counters, which are basically sequential circuits, and you can have a connection between them. So when you are building a real digital system, for example, a CPU, there will be a numerous number of such units. There will be a numerous number of such functional units as well as memory units or data units with interconnections between them. So even though for small circuits, you could design at the gate level, For designing such complex circuits, you need to look at a higher level of abstraction, which deals with blocks of or functional blocks or functional memory units. So you need to look at a higher level of abstraction. When you go to there is something called there are many levels of abstraction, just like a normal software program. But we may discuss a little bit of something called a register transfer level of abstraction. Okay, so one level of abstraction that is commonly done is that all these circuit, whatever the circuit elements you have, you consider them as belonging to two parts. One part is called a data path, which consists of some registers which stores values, maybe counters which stores values, and then their arithmetic operations or logical operations like adder, comparator, multiplexer, these operations. Okay, so this is a set of values, data values stored in registers, along with their functions or functional units that are used to operate on them. This part of the circuit, they may contain both combinatorial and sequential. This part of the circuit is called a data path. It's just an abstraction for the circuit elements which consist of register, adders, comparators. And there is another path of the circuit which is called a control path, which basically controls the timing, the sequence of operations that you perform using elements of the data path. Like first you add these two registers, content of these two registers, then you compare the content of these two registers. So it's like a flow chart. It's the sequence of operation that are performed inside the data path. So usually what is done, the data path is kind of, it's not a fixed circuit element, fixed function. It's a collection of circuit element, and the control path determines in which sequence these circuit elements will activate and compute something. And depending on the sequence in which they are activated, you realize different operations, you realize different functions. Okay, so that's the abstraction, a data path and a control path. So let's take a simple example to explain. So this is a simple flowchart to compute product of two numbers A and B by repeatedly adding them. So let's say the A and B are two numbers. We want to compute A times B. P contains the product. You initialize P to 0 and then keep on accumulating P equal to P plus A B number of times. So how do you do that? You decrement B every time till B becomes 0 and add P equal to P plus A. So basically P will store A into P after this, and then you stop. So this is a simple, let's say you want to build such a multiplier using digital circuits. So let's see what are the data paths and control paths for this. So data paths, as I have told you, these are nothing but the registers which will store values and simple arithmetic operations. So what are the registers here which will store value? Here A and B is a register, so I'll have A and B in my data path. I'll have P in my data path, which stores the product. And what are the operations that we need? We need a comparator here. Oh, no, this is a data load. P equal to 0 is a data load. We need a adder here. We need a decrementer here, and we need a comparator here. So these are the elements we will need in the data. So data path will consist of three registers, A, B, and P, and three operations, adder, a decrementer, and a comparator. So equality comparator. These all will be the part of the data path. Now the control path will decide in which sequence these operations will take place. So let's look at the data path first. This is an example data path. So I have two registers, A and B. Sorry, A and B, I have two registers, and P stores the product. I have the adder, I have the comparator. And this is the external data input, that is, will get the value of A and B. And there's a bus, which is an interconnect, where the contents of these registers will be stored, and the external input can also be stored. Maybe the output can also be read out from here. Okay, so let us think of the sequence of operations that we can do. So first we'll load A. So this data in will have the values in the bus. Okay, so now each of these registers or maybe adders and comparator, they'll have some control inputs. So this register A has a control input load A. This register B, P has a control input load P. It also has another control input clear P, which will probably need for this P equal to 0. We'll need a clear P. Okay, and this B will have again two control input. One part will be a load B, which will just parallelly write the values to the register, and then decrement B, which will decrement the value by 1. So these are the control units, control signals that are required by the data path element. So what we will do, depending on our timing, depending on our flowchart, in sequence, we'll send different values of these control units so that the final result is obtained and this flowchart is implemented. So let's see what sequence we want to do. So the first sequence will be, we'll activate load A. We'll activate load A, we'll send load A equal to 1, and then data will be loaded to A. Input data will be loaded to B. Then we'll activate load B. Data will be loaded to B. Then we'll activate load P. Oh, no. Then we'll clear B. Then we'll clear P. Then we'll clear P. So P will be set to 0. Then in a loop, we'll keep on adding B. We'll load B, keep on adding B. How many times? B number of okay, so every time you add A to B, you keep on decrementing B. Finally, you see when B is equal to 0, B is equal to 0, you see. So this equal to 0, you see, this is an status signal, whether the loop has been completed. This is a status signal. So the control path will look into the status signal and decide the timing, how many times this load A, load B, decrement B, this should be operated. So let's see what the control path does. So let's say the control path starts with start, then activates load A, activates load B. Simultaneously, it can clear P. Then it decrements B and does the addition. That means loads P. Okay. Then it checks for B, does a comparison on B. If B is not 0, it goes back and does this. If B is 0, it says stop. So you can see this flowchart I can represent by a finite state machine. And I can assign states. Let's say S0 is start, B did A data in is S1, S2. So like this, we can assign states. And then this flowchart is, then we have a loop. We have usual transitions here, and except for this loop in state S3. So you see this FSM just represents this data path. And this FSM, I can just, as we have done before, we can realize this FSM using a set of flip-flops and combinatorial clouds. You can realize this FSM. Okay, so this FSM will transition from the states to state, produce outputs. Can anybody tell what are the output of this FSM? What would be the output of this FSM and what will be the input to this FSM? Anybody? Can you please tell? So the output of this FSM will be the control signals. Load A, load B at different point of time, different sequence. You can easily draw the timing diagram. I'm not drawing the timing diagram. At different sequence, these outputs, load A, load B, load P, clear P, all this will be generated. And this control path, the status signal equal, B equal to 0, that comes from the data path, and that's the status signal, which is an input to the control path. Control path has one more input, which is the data in. In fact, the data in is the input to the data path also. And then you have a clock, the same clock for both. Okay. And then you have an output start state when it is to start and output done state. So this will be the connection between them. Okay, so this is a simple example of a. So what we are doing basically is that we are doing the same thing. We are still doing a digital design, but we are doing it at an abstract level. We are doing it at an abstract level. So where you can the whatever you want to compute, you write it down as a flow chart, and then write it down as a data path, control path, and then you realize your data path and control path using the circuits. This is the complete part of a complete flow chart of a or steps of a digital design. So as I have said that this diagram, this control path diagram, you can actually represent it by something called an algorithm state machine, algorithmic state machine, or a ASM, sometimes also known as an ASM chart. So ASM chart is just a flow chart, which shows the actions and the control flow, plus some timing diagram, plus some state diagram. Okay, plus some timing and state diagram. So that's the only difference. So it's the difference between this flow chart and this control path is just the control flow, but the timing diagram, when I mean in what sequence, what are the clock instances where this should happen. This is just a timing diagram. Okay, so let us explain this algorithmic state machine or the ASM chart in more details. Once you have the ASM chart, it's very easy to convert it to an FSM, and then you have to realize the FSM, which you have already discussed, how to realize an FSM. So what the algorithmic state machine will do is that if you write down your computation as a flowchart, it's very easy to convert it to an ASM. And the ASM, using computer-aided CAD tools, it will automatically convert it to the FSM diagram, or rather something called a register transfer level abstraction. And then further downstream processing, this RTL definition using Verilog, this will go down. You know how Verilog, it will be converted to a circuit design, and the circuit design will be optimized, and that will be converted to an wiring design and layout design, finally to the physical design of the silicon in the chip. Okay, so let's see what this ASM is. So let's see what are there are three components that you use in ASM to write down these ASM charts. One component is something called a state box. It's a state box. The state box consists of a rectangle with one input and one output. And in the top left corner of that box, you have the name of the state. Some state name you can give, and you have the name of the state. And inside the box, you have the output signal. Remember, everywhere we are sending some output signals. Have the output signal that is produced when you are in this state. So you can imagine that this is just a mood type, because at every state you are producing an output. So it's a mood type output. Then you have decision boxes. What is done in the decision box is that you are coming from some state, and then it does a condition check. Okay, it does a condition check. So which is the value of a register, or value of a single bit, or value of an output, whatever. It does a condition check, and depending on it's true or false, you take one of these two paths. You take one of these two paths. Right. Say, for example, you are decrementing B, you have a comparator whether B equal to 0. If B equal to 0, then it's done. Otherwise, you keep on looping. This is a decision box. Just like C program, the convention is you just write the variable. You just write the register or the bit that you want to check here. Meaning that if bit is 1, then something happens, otherwise something happens. Then you have a conditional output box, which is a Miri type output, denoted by this kind of symbol, a rounded rectangle, which is that it's a conditional output back. Why conditional? Because when certain input comes, you are in a state, and then certain type of input comes, then you take certain action or produce certain output. Then you take certain action or produce certain output. So it's a conditional output box. Whereas this is a Mealy type output, this is a Mood type output. Okay. In fact, there is. Let me explain in little more detail. So this is the state box indicated with a rectangle. This is equivalent to a node in a state diagram. The state box is nothing but a node in the state diagram. We'll see when we map a state diagram to a node, we'll see, and vice versa. We are required to do a two-way mapping. We are required to map a FSM to a ASM as well as an ASM to an FSM. Okay, so this box is equivalent to a node. The name of the state is written on the top left. Mood type outputs are written in the box. And we only list the outputs which are set to 1, which must be set to 1. We only list the outputs which must be set to 1. If some variable or a register is not written, it means it should be set to 0. Then you have a decision box. This is indicated by a diamond. There is an so one thing you notice here, there is an output signal. Okay, so only the outputs that are set to 1 are written down here. Okay, and this we may need for further processing. Okay, one way you need it for further processing is for testing certain condition. So you have some condition expression or a variable or something, and depending on the outcome of the condition check, you take one of these two paths. So this is called a binary decision box. It's called a binary decision box. Of course, you can use shortcuts, like you can just write W, meaning W equal to 1. You can also have a vector decision box denoted by an hexagon. So here the condition check is on a binary vector Z, and so input is a binary vector Z, and you can have multiple conditions Q0. And since this is a binary vector, for different combination of values of this binary vector, you can have multiple outputs from this decision box, multiple paths, outputs from this decision box. Okay, so that's why it's a hexagon, it's a vector decision box. And then you have the conditional output box, is denoted by this oval. It's a Mealy type. It writes down. So you see, when you are representing an FSM, it can be either a Moore or Mealy type. So either case you can, and since these are equivalent, you can actually write down an ASM with only state boxes without conditional box, but it will be a larger ASM. In practice, we will need both, so we have a provision for the conditional output box also. So the output here will depend not only on the state variable, but also on the input. Okay, so this is the output that is generated. Now, okay, so let us see an example. So for example, I have one value coming from the decision box, and depending on the input, I can, by the way, what these actions or output meaning, you have already seen here, many a time these actions or output will be some load or clear commands. The action of the output of the control path will be some load or clear commands, which we call register transfer, or register writes, or register outputs, register reads. So you see here, these are all register writes. This is register clear, which is kind of a register write. So these output boxes, the actions will often be register transfers. They may as well be outputs. So for example, you have reached the end of the program, you want to output a done state, or you want to output the result. So this may as well be the output, but internally they may mean register transfers. Okay, so so even for the state boxes, you can have register transfers as output, but state boxes are mode type and these are milli type. Now let us see these three types of elements, these three types of element and in the ASM, how we can connect them up, how they connect them up to form the chart. Okay, so the following things we need, since this is a more detailed diagram than a flow chart, when we connect them, we need to mention the following things. Or rather, the connection specifies the following quantities. What are the inputs to the system? What are the outputs? What are the conditional outputs? What are the register transfers of the operations that are happening? And what are the conditional transfers that are happening? Okay. So this register transfers can also be a move type or a milli type. Let us see an example. What we'll do. Okay, one more thing that is usually done. So these things will specify how they are connected. One more thing that is usually done, you form what is called an ASM block. ASM block. So ASM block consists of a state box, along with all the decision. This diamond decision box and the oval, which is a conditional output box, which is associated with the state box, state box. Okay, so for example, this ASM block consists of the state idle, consists of the condition check start, consists of the register transfer outputs, these two register transfers actions, along with one more condition check, Q0. Okay, so this entire thing would be called an ASM blocks. So what does this ASM block tells? See, while I come out of this ASM block, I move to this possibly move to this one of these two other states, the mal0 or mal1. I can move into any of these two states. So what this blocks determines, it's kind of, this block represents one single state, and once you come out of the block, you move to another state, which may be another block, another ASM block. So one state, along with the condition checks needed for transition from that check, along with the actions, output actions or register transfers that are done while transiting from that state or while inside that state, consist of an ASM block. Okay, so now let us see some example. Okay, by the way, once you have got this ASM chart, it is very easy to come up with the timing diagram of the different registers, values of the registers that are involved, or the states that are involved. Okay, so so the rule is simple. The output will appear while inside the state, while still in the state, in that part of the time. Register transfers appear at the clock while exiting the state. New values appear. So there are three actions. So first thing, if you look at the timing diagram, first part where you are inside a state and output will appear. At the clock, when exiting the state, the register transfers will take place. And when you are in the next state, the new values of the registers will appear in the timing diagram. Okay, so let's take an example. So this is the clock cycle. This is the start signal. So start signal starts at this clock cycle and stays on forever after that. These are two registers or two variables, 1-bit registers, you can say. They are throughout 0. These are inputs which are 0. And then the states change like this. So this is an idle state. Okay, this is an idle state. And then you move to the mal state. So these are the timing diagram of the states, and similarly you have the Abel diagram. So note that we are drawing these kind of small slopes because there is a transition time from the logic to go from one level to another. Okay, similarly, you can values of the other register. So you can easily find out the timing diagram from the ASM chart. Okay, so let us take some example how to draw these ASM charts. So what we'll do, we'll draw the FSM along with the equivalent ASM chart for that FSM. So let's look at this FSM here. So there's an initial state reset, it starts from there. Then there are three states A, B, and C. And in these states, it has a mood type of output, z equal to 0 when within this state. And there is a Mealy type of output. Okay, where you are transiting, the on receive. Oh no, I think W is there. Oh no, W is an input. Sorry. W is an input. Depending on the value of W, you transition. So this is a diagram. You can see here that you start from reset, then you move to state A. Then you are just walking through the FSM. You are moved to state A. Then you output Z equal to 0. Okay, Z equal to 0, so it's not listed here. The 0 variables will not be listed. Then I'll check the value of 1. Sorry, I'll check the value of W. If W is 0, I stay back in A. I loop back to A. If W is 1, I move to state B. B again outputs Z0. So nothing is listed here. Again, I check the value at next clock. I check the next clock edge. I check the value of W. If W is 0, it goes back to A. If W is 1, it moves to C. At C again, at C again. Okay, so now you produce a Z. Because Z is 1 at C. Now you list Z. And then again you check W. If W is 1, you loop back to C, else loop back to A. So this is the ASM chart that we have for this FSM. Let's look at another example. Oh, okay, so here, so this is a kind of completely Moore machine. So now let us look at a Mealy machine. So again, you have three states, A, B, and C. And the output Z, input is W, output is Z. Now you see the output is dependent not only on the state, but also on the input. So this is so now I have a conditional output block. This is Mealy, I have a conditional output block. And the output Z is 1 only when you are at state B and W is 1. So you are at state B and W is 1, then only you have Z equal to 1. Rest of the same is simple. You start with reset and move to A. Z is 0, so I have not listed it. Check your W. If W is 0, you loop back to A. Z is still 0. If W is 1, move to B. And B again, B again, you check the value of W. If W is 1, then you output Z equal to 1. Else you loop back to A. Okay, so this is the very simple. I mean, you can, it's just this FSM along with the sequence in which things happen, along with a algorithmic steps in which they happen. It's just the FSM written in a algorithm form or a flowchart form. That's it. So all you need to do, I think you have already done this. It's very, very simple. You have already, when you interpret an FSM, you look like a flowchart. This happens, then this happens, then you check this, then this happens. All I am doing in this FSM chart is just writing down this flowchart, the way I interpret the FSM. The advantage is that since I have the timing sequence here, I can easily design my data path and control path directly from the ASM. So can anybody tell what will be the data path and what are the components of the data path and how will the control path look like for this ASM chart? Just to show that it's very simple to convert an ASM to a data path and a control path. And of course, once you have the data path control path, you have to convert it to the logic, the design and the gate level design, not the register level design. Okay, so what's the how do you design the data path? What's the data path and control path for this ASM? Anybody? How do you draw the data path and control path? What are the components of the data path? Let me try to draw. What are the components of the data path? So let's say this is my bus. And what are the components of my data path? So I'll have registers A
and B.
B. Anything else? Do I need something for Z? Do I need something for Z? Okay, what are the functions I need in the data path? What are the functions I need in the data path? And maybe I have an data input, which gives me W, and maybe a data output also, which gives me Z. Okay, and this will have a load input, and this will have a load P. Do I need anything else? No. Okay, so can you tell me what is the what anything else, any arithmetic or logic you need, logic function that you need? Any arithmetic or logic function that I need here? Do I need a comparator? So I'll need a comparator. Okay, so I'll need maybe a comparator for W, which will check whether W is 1 or 0. It's not really a comparator. It's just maybe you can use it as a line also. Maybe I can use it as a line also, as a where if you have another way of representing this, you have your W, then you have a line which checks the value of W. Oh no, for A and B, do I need this? No, I don't need connection to the bus. Okay, so what's the control path? How do I design the control path? What will be the sequence of action in terms of the signals load A, load B, or compare W, load W? In terms of that, what will be the control sequence? What is the control sequence we need? Okay, so first what will happen? It will be in state A. Achha, do we need A and B as registers? Do we need A and B as registers? I don't think we need A and B as registers. We need W and Z. Yeah, repeat.
Sir, if we have only one flip-flop, it can...
One flip-flop would do, right? One flip-flop would do. Okay. Okay, one flip-flop would do. No, so what I'm trying to say is that that flip-flop which controls you are moving from state A to state B, that would be part of your control path design. Whereas that's the point I want to drive in. So data path will consist of only the parts which stores some values and does an operation, arithmetical logical operation on these values. That's all. Whereas the state transitions, they will be part of your control path. So do you need A and B in your data path, or should you have them in your control path? Or rather, do you have W and Z in your data path, and A and B in your control path? So can I instead do it like this? So my data path consists of these registers W and Z, and maybe a comparator, and my control path involves a state transition, which can be implemented using a flip-flop of A and B. Okay, and what are the values that I need? So if we have external input, suppose I have external input W and external output Z, So how would I, and now there are connections. So there are load W, load Z, or Z actually I don't need to read, I need read Z, and load W. And these are my interconnects between the interface between the data path and the control path. So my interface would be load W, read Z. Anything else? Any other interconnect I need between my data path and control path? So what I'll do, I'll start with reset. Maybe I need another state called reset. I'll start with reset. Then my control path will be, the FSM will move to A. Then when it is at A, it will load W. From the bus, it will load W, looking at the external input. And then compare W, check the value of W. And then this is I also need a status signal about W. This is a status signal about W. Maybe I need a status signal. They say W equals Z, equal to 0. W equals 0. I need a status signal. Okay, and depending on the status signal, there will be transition between A to B. And when finally you get the value of Z, you enable this read Z, and that will be going as the external output. So I think this gives you the idea how to do it. So this is a slightly more complicated FSM chart, ASM chart. So there are 4 states, idle, GNT1, GNT2, and GNT3. And you have you have certain outputs, G1, G2, G3. These are mood type outputs, that's why they come here. And then you have these inputs on which you are doing a condition check. So they come here in these decision boxes. They come inside these decision boxes. And based on the decision, you have the state transition. So maybe one small exercise you can do is to draw the control path and data path for this ASM chart. Okay, so here is the summary. So these are the steps. You first, when you have to implement a digital system, you first write down an algorithm, a pseudocode, to describe the desired operation of the device. So say maybe you want a traffic light controller. You write down the algorithm for a traffic light controller. Or maybe a elevator controller or a vending machine controller. You write down the algorithm as a pseudocode. Then convert the pseudocode to an ASM chart. It's very easy. It's already in the form of a pseudocode, so you can easily convert it to a flowchart. Now this part is non-trivial. This part is almost kind of unique. Given a pseudocode, you have only one ASM chart, almost close to the same similar ASM chart. But this part, several possibilities are there. Designing the data path based on the ASM. So what are the variables, what are the inputs? So this part, but it can be automated. You can convert this ASM chart to a data path. Okay. So now, now ASM charts can be at various levels. So you have a maybe higher level of abstraction ASM chart. Once you design the data path and have your registers, you can rewrite the ASM chart with involving the registers and new state definitions. Now, once you have this detailed ASM chart, now you design the control logic based on this detailed ASM chart. So what I suggest is that for any one of these examples, you can go through this process. Okay, or maybe not even this. One of the lab examples that you have given, maybe a traffic light controller. You can go through the steps and finally have the logic design. You will see it is much more structured, and in fact it can be automated. So all the CAD tools should use this ASM. Okay, so I think that's the end. This gives you a high level view of what is to be done with all these things that you have studied. How to go about a digital design, how to optimize a digital design, how to realize a digital design using gate and flip-flop elements. And the moral of the story is there are different levels of abstractions of a digital design. Just like you have an assembly language and a high level language, there are different levels of abstraction. And in the industry, if you work in a chip design company, say Intel or NVIDIA or ARM, you would go through all these steps down to the silicon level, starting from a very high level requirement. Okay, so and all this theory that we have taught, all these state machines, Moore machines, minimizations, everything comes into picture everywhere. One thing is that most of these parts are automated. There are CAD tools which will do most of the parts for you. It's humanly impossible to do for a large circuit. They are done by CAD tools. But the overall design, we have not talked about considering elements like power, time, clock speed, and many such things. The overall design, it's still an human art. The more you get experience, the better design you are at. All these tools, all this mathematics is there to help you. But at a very high level, it's still an human art. Of course, you'll study in more details as you go into your computer organization course or the architecture course. We'll study all this in a lot more detail. But the goal of this course was to tell you about the gate level and the flip-flop level, the mathematics, the Boolean circuits, how to realize them. And these are all your building blocks for designing more complex systems. Okay, so with this we end. Thank you. I think that the date, one announcement, the date that has been mentioned to you in ERP for the exam, that's the date of the exam. So
yeah, that is, I think, all of you have received that, isn't it? So the exam for slot C, I think, is scheduled at 8 o'clock in the morning of the 13th. Can you just check and confirm?
Yes.
Hello. So yeah, so it is 8 o'clock. 8 o'clock on 13th of April, I think. Yeah.